Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Thank you so much for coming. My name is Karoy Banco. I'm a researcher here at Microsoft Research, and it's my great pleasure today to introduce Evan Suma. He's visiting us from USC, from Institute of Creative Technologies down there, and he's one of the world's experts on all sorts of VR trickery, trying to basically understand locomotion, expand our spaces in kind of walking abilities and manipulating abilities in VR, mostly by manipulating what you see and what you get and the differences between. But I won't take much from his talk. I just want to welcome and say, thanks for coming down and giving us this presentation.
Okay. Thanks, Benko, for the introduction. So today I'm going to be talking about how to make a small space feel really large. So this is all about perceptual illusions in virtual reality, but with a practical spin, because what we're trying to do here is solve a real engineering challenge for VR. So VR for me is a really kind of special place to work. So ever since I put on my first HMD, I became fascinated by the experience of being in VR and creating VR experience for others. And what really ups the ante for me is when you can use VR as a medium to create really surreal experiences that transcend what is possible for the real world. So some people say recreating the real world in VR is kind of the holy grail, but for me it's transcending the real world, going beyond what we normally can do. So as an engineer, I think this is a really challenge. Being able to do this is really challenging because VR has so many moving parts that need to work. As a researcher, it also is a really interesting empirical tool for the controlled study of human perception and behavior. You can actually use it to test things you can't evaluate in the real world. And this talk really is about the intersection of these two goals. It's engineering magic experiences, but experiences that also enable us to do the empirical study to understand more about the human experience. So, an overview of this talk, I'm actually going to first take a step back from that and focus more on kind of just some of the work that we did in just the fundamental display technology, because VR, these experiences are technology mediated. And then from that, I'm going to move into kind of the challenge, the next big challenge that I see that we're trying to work on, and how we're kind of looking at this from the perspective of what I call hacking human perception through a couple different types of illusions. And then finally, I'll talk more about the practical spin of this, which is how to enhance interaction fidelity, which is kind of my code word or my technical term for creating magic. So looking back at kind of when I started in VR, so I started in 2004-ish, 2003, but I got really started grad school in 2005, and these were the displays that I were using at the time. So we're talking pretty low resolution, 640 by 480 per eye, bulky, heavy, very expensive, but probably the most problematic at the time was the field of view. So the V8, kind of the standard that you saw a lot was 60-degree diagonal field of view. And so if we look at this this is actually mapping what that type of field of view is onto your retina and what your human visual system can actually see. It's like looking through a very, very small window. And this is for me why VR up to that point, all throughout the time I was studying in graduate school, really wasn't magic. In fact, a colleague asked me when I got started in VR, and I told him the year, and he said, "You decided to get a PhD in VR when VR was down and awful? What is wrong with you?" So I guess I just liked a challenge. So. So this changed for me in 2010 when I moved to the Institute for Creative Technologies, and we have a prototype display there called the Wide 5. And so this one really, and the antlers there are kind of funky, but they're just for the motion tracking system. But the real fun thing about this display was that was when I first experienced VR magic, because it has 150-degree wide field of view. So the difference here, you can see that it really is the difference between looking through a tiny window at something distance and really, for me, being there. And so if we look, that wasn't the only display capable of doing that, although it was the widest at the time. But if you look at the cost, you can really see two categories here, and it's really useful to look at this as dollars per degree. So if you look in the bottom, that is kind of more what we would target as, not even necessarily consumer level, but more affordable HMDs but their field of view was really limited. And getting up anything over that 60-degree mark really ended up, it did not scale linearly, and it ended up getting extremely expensive beyond what a lot of research labs can afford, let alone the average person. And so a lot of our funding at ICT comes from the US Army. And so we had, in about 2009, the acquisitions people who were in charge of all of the purchasing and decisions for the Army came to us, and we gave them all the demonstrations of VR, and they said, this is all great, but it will never be used by the Army, and the Army can invest in VR, because if we want to train people, we have thousands of people we need to train, and it's just too expensive. There's no way. You have to figure out a way to do this in a more cost-effective manner. So this kind of started us and got us thinking, and we were really inspired by this little piece of technology here, which I don't think has gotten kind of forgotten and doesn't get a lot of credit, but it was kind of a little before its time. So you could actually get this at like Target or Walmart or Amazon at the time for less than $20, and it was a little plastic device from Hasbro called My3D that you could slide your iPhone or iPod in, and you could get a 3D experience. But it really was, from a product perspective, not successful because it was a capability with no content. But we got really sort of interested in this and in the possibilities that now the smartphone screens were finally getting big enough and high resolution enough where we could actually start doing interesting VR experiences with them. So we did, this is a kind of a prototype system that we published at IEEE VR in 2011, which combined this with a Bluetooth keyboard for interaction and a few other moving parts. So this kind of got us thinking about this, but then the real kind of insight was really when we started doing this with higher end optics. So this is some Leap optics that we pulled off of an old boom display back from the 90s, and then we basically just cut out wood and slapped two iPhones in front of it. And there were all these problems with it. There's distortion, the eyes are not synchronized properly, but the real experience is when we took this live demo to the conference and we started handing it to VR experts, and they were looking into it for the first time and seeing high-end optics in front of these smartphone screens and being like, wow, I didn't think, the reaction we got from most people was, I didn't think it was going to look this good. So we left from that and we really started thinking about, okay, there's something here. We really have to continue trying to make this accessible. So the next year we came out with what we called FOV to go. If you've been to IEEE VR, you might have seen us hand these out. We brought about 200 of them. They're foam core laser cut ones with lenses that are basically $1. And then you just basically fold up your own cardboard display, and we have them for all different types of phone models. So this, at the time, this was really, really kind of an exciting thing. Today I show this, but it's more of a historical kind of note, because now, of course, Google Cardboard has really gone and popularized this notion of smartphone VR over the last couple of years, and that has really just been an explosion in terms of that ecosystem that I think is really, really spectacular. In parallel to the smartphone VR effort, we were doing some really prototyping on the HMD side, and we wanted to really start building not just viewers, but head mounts. And so we found this hobbyist, we hired him, his name's Palmer Luckey, and he was a hobbyist teenager working in Los Angeles who had quite a eBay VR HMD collection that he was playing around with in his parents' garage. So we brought him in the lab, and we started to build prototypes here, which we referred to as Franken HMDs, which were basically cobbled together from eBay parts from different displays and LCD panels you could buy online, and literally held together with tape. But they really we started to see we can start to build this for about $300. And so we decided to open source all of this. So all of these designs, the socket HMD is kind of an interesting historical note. I think the consumer market is now, has gone leaps and bounds beyond this. But it was our 3D printed design for this display, which was very similar to the Oculus Rift DK1. And we started to move beyond the cardboard to 3D printed phone viewers, as well as tablet viewers, which are really interesting because now you can combine an immersive display with a touch surface and do a hybrid interaction where you can actually use some manipulation of objects on the screen while you're looking at it. So all of these are available on our website, and anyone with a 3D printer can download and create them. But there's only a limited amount of people. I love open source and I believe in it, but it only touches so many people. And what really was the catalyst for this explosion was when Palmer sent one of those prototypes to John McCormack and then left the lab to do a Kickstarter, and the rest is history. Oculus was eventually founded and bought for Facebook for $2 billion, and now Palmer is being one of the lead spokesmen for the field of VR. And one can make the argument that though this was really one of the catalysts, really the real reason was that the display technology had gotten low cost enough, and other, of course, companies were looking at this at the same time as well. So it really was something that, though this was a particular catalyst, this is something that I think was just inevitable based on the cost of technology display technology going down and the quality going up. And you can really see this, I think, when you look at that chart again and you put the Rift, socket, and other consumer level HMDs on the $ per degree mark. We're looking at that 90 degree vertical was kind of the initial version of the Rift. And what we see there is that that's getting pretty good enough. And the $ per degree is so much lower than everything else that really now we could go back to the people at the Army and say, you can now afford these. And so now we can start to really see people care about VR, and of course now there's so many companies, HTC, Sony, and all of the other ones. I don't put Microsoft on this list because HoloLens is a mixed reality device, which of course is similar, but it's in its own class. And this talk is really more about VR. So can we say mission accomplished? Is VR a solved field at this point? And so I'm giving this talk, so hopefully it won't be surprising that my answer is no. And the reason is, I think a lot of the content creators and a lot of the experiences that we're seeing coming out, at least right now and in the last several years, have interactions that look like this. Seated use or movement in a very, very small area, and a lot of the interactions are mediated by controllers, gamepads, or other sort of handheld devices to move through a virtual world. This, to me, I've done this, now that I've been doing this for well over a decade, when I have these kind of experiences that are mediated by controllers, and it just feels like a video game to me, this does not feel magic anymore. And I worry that in the long term, that once the novelty effect wears off, that people have been immersed enough and seen enough VR experiences, it's not going to seem magical anymore. It's just going to seem like another type of gaming. So,
that experience, do you still get nauseated from induced motion?
I'll talk about nausea in a little bit, but yes, that's also another problem with these kind of locomotion metaphors, is that motion sickness, because your motions don't map with what your body is doing. That is a problem for some people, at least some people. So why is walking a problem? Well, it should be pretty obvious that even if you have a tracking space that can allow some physical body movement, if you want to walk through a large virtual environment, say a virtual city or a large office space or what have you, at some point you're going to run out of physical space. You're going to walk and you're going to, in the best case, we're outside of your tracking area. In the worst case, you're going to physically collide or walk into a wall. And because you're wearing a headset, you won't be able to see it. So this is kind of one of the real fundamental challenges for any sort of VR system, is this real problem of physical locomotion through the environment. So we researchers have been studying this for a while. So this has been something that people have been thinking about for quite some time. And so there is one interesting solution that came out of the literature about 15 years ago. So this is not my work. This is the original redirected walking work, which comes out of UNC Chapel Hill. Which really, I think, has been an inspiration for a whole class of research in the field. And the basic idea here is that you just decouple physical and virtual motions. They're related to one another, but if you, for example, get someone to walk through a zigzag corridor, you can actually get them to walk back and forth in the real world. And if you just realize that there is that you don't have to have a one-to-one mapping between physical motions and virtual motions, there's a lot you can do with that. So let me give you some examples of how this works. So the easiest way to do this, or the original way that Sharif suggested, was through what's called manipulation of gains. So a gain is just a multiplication factor applied to your motion. So in the case of rotation, I might walk through a virtual space, and then in this example, rotated, I'll show you that again, rotate 90 degrees in the virtual space, but 180 degrees in the physical space, so that you can, after your turn, you are now walking along a different vector. You can do this in other ways. Another one that's been identified is called curvature gain, and in here it's different because you're walking straight and there's a continuous kind of rotation applied as you walk forward, and you will bend and walk along a curved path. And then finally there's translation gain, which is just basically a multiplication on your step size, but only in the forward direction, because you don't want to amplify side-to-side movement. So you can travel greater distances virtually than you are physically. So why is this better than using controllers? And the reason is it's because it's linked and controlled to by your own motion. And so there's two different perceptual systems in place here. One is your vision, and one is your vestibular sensation, your sense of balance, your body's sense of what your movement. And turns out that vision tends to dominate when those two senses are in conflict, as long as they're kept to within a certain threshold. So there's been researchers who have studied this, and so these are just some of the kind of numbers out of the literature. And it turns out if you do it within these parameters and do it the right way, then not only is it imperceptible to the user, but it also hopefully won't make them sick, as long as you just don't do this too much. Now, I can tell, having been in these environments where you do it too much, it can make people sick, so that is a concern. But the key here is that vision dominates over your sense of balance. So one of the things I wanted to do was really kind of understand, not just kind of do I notice these illusions, but how does this impact my sense of spatial orientation cognitively? How does this impact my experience of this virtual world? So this is an experiment that we did where we were pointing at targets. So what happened in the beginning was you see a virtual target and you aim, and we're using a tracked wand to aim. And then you point at a real target. So they bend up the optics of the display, look at a real target in the real world, point at it, and then they're asked to remember where these are. So point at the real target, point at a virtual target. Then you're back in HMD. We go through some sort of virtual experience where we apply these redirected walking techniques. So for the sake of simplicity, I'll just show you, it would happen continuously, but at the end of that walkthrough, you're 90 degrees offset from where you were when you started in terms of your physical orientation. So if my original virtual target was there, we wanted to know, would you point at that virtual target where you originally saw it, or would you point at it in its position as if it were redirected? Basically, is your memory of that your orientation of that target now 90 degree offset? And more interestingly, what would happen to your perception of the real target? Would you point it where it was you originally saw it, or would your reference frame in the real world move as well? Another way of thinking about this is, are you maintaining two models of your spatial orientation? Do you have your real or your virtual? Or if I manipulate the virtual, do I manipulate also my real? And so the way we look at this, we have to figure out how do we measure this quantitatively. So the way we looked at it is looking at angular pointing error. So this is a way of doing this. This is a pretty common metric in VR. And so what we looked at, what those positions were, we calculated the angular pointing error. And so what we found is actually exactly what we would expect if they were correcting for that the redirection, and they were moving those targets reference frames. So for both virtual and real targets. And the way we do that is just we can see that the angular error, so this is, the lower this is, the more accurate. Those angular error are pretty consistent with what you get with just regular pointing. So those numbers 35 to 40-ish are pretty typical of just the angular errors you get when you're asked to point to something. Whereas you can clearly, there were about 90 degrees offset from what their original positions were. So this was a really cool result for us because this confirmed kind of or resolved an argument that I'd been having with Mark Bolis, my colleague and co-director of the lab, where he maintained adamantly that there were dual models, and I said, no, if I mess with you in the real world, I think I'm going to be able to get you to your reference frame in the virtual world. Real world's going to shift as well. And this kind of resolved that, and he stopped complaining at me. So now I want to start talking about another class of illusions. So this type of work with redirected walking really kind of was just the initial insight that what happens in the virtual world can really transcend what happens in the real world, and we're not bound by the same laws of physics. So now let's talk about another type of illusion that I kind of just came up with, and I really got this inspiration from the kind of common psychology kind of stuff you see in Psych 101. And here's an example. So I'm going to ask you to look at this picture, and then I'm going to change something. I'm going to ask you to just call it out if you see what's changed. Anyone notice it? Just call it out if you saw what I changed.
The building is better away.
Here, I'll make it really easy. And so the reason that's difficult is because the human visual system uses motion to be able to detect changes. And just that split-second interstimulus image, that black screen, disrupts that perception of motion. And then it becomes very, very hard. And this has been well studied for many, many years in psychology. It's called change blindness. And it's very, very consistent across people and a very powerful illusion. So I started to think, what happens if we apply this to VR? And so here's an example of how this works. So in this example, you're going to see walking through this virtual room. And watch what happens on the overhead view on the top right, left as they approach this desk. So they were looking forward at the desk, and in this study environment, they were just kind of looking at pictures. But what happened behind them was that this doorway moved 90 degrees. It stayed in the same location, but the orientation of the doorway swapped along the corner. You're about to see it again as they walk to this corner of the desk. Oh, whoops. Okay, so the key here is that this manipulation occurs behind their back. So everything appears consistent to them in front of them, but when they turn around, the door is just offset by 90 degrees, and the corresponding hallway is also offset by 90 degrees. This basically means that within about a 15 by 15 foot space, I was able to infinitely repeat this and do a 3,600 square feet office building within less than 200 square feet. And this is basically, because this is a consistent illusion, as long as they're going linearly and entering into these rooms and kind of not looking back, like walking at the door and like staring at it while walking backwards, which people never really do, but they'll never see it because the manipulations occur behind their back. So this was a really interesting illusion. I wanted to test it. So I ran several experiments, and I was really trying to get some statistically significant results of how many people noticed this. And what I really found was that I completely failed in getting statistically significant results because no one noticed. So I did this to them throughout this environment 12 times each, multiple experiments, and 1 out of 77 people noticed or reported that illusion. Even after it was disclosed to them afterwards, we tried to tease it out gradually with questions, and it was so effective that we were not expecting it. So this was really, really interesting. So we started to look at kind of how this affects your perception of space. Okay, you might not notice it, but what do you feel that this environment looks like? So as they're going through this environment, which cannot be represented with a single drawing because it's a dynamically changing world, but we asked them to sketch map it. And these are kind of very consistently across the study the types of maps that people drew, which look very similar to kind of the conceptually this kind of office space with the, kind of in the square environment. So what this, and we analyzed these through some subjective ratings and statistics, which I won't get into here. But what we really found overall is that these spatial inconsistencies just seem to get resolved. Perceptually or cognitively, when you're going through this environment, as long as your experience, my takeaway was, as long as your experience is locally consistent, then kind of globally, we figure out a way to make this work. When you're forced to draw a map, you figure out a way to make it fit on paper. Yes. So these were drawn after the experience ends, immediately afterwards. Yes.
So this is sort of interesting to me because as long as they do the path where they go in every office, this will work. But if it's sort of an open world where they can explore however they want, it won't work, right? So
that's correct.
So it seems like in order to decide what you need to do, you almost need to be a little predictive about where they're going to go, so you can kind of start manipulating the world ahead of time and manipulate them later or something.
Yes, yeah, you are 100% correct, and that is the latter part of my talk, which I will directly address that question. Yes?
So during your study, did the participants saw the space before they try, or they wear the headset before they go inside the space?
In these studies, we did not blindfold them before they entered the physical space, so they did see the physical space beforehand. So, yes?
Did you do a kind of longitudinal study on this in terms of people adapt to technology and their skill sets change and their way they perceive things change? Any information on that, whether people over time would actually mature and understand it differently?
Nothing beyond anecdotal. So I'm not really aware of longitudinal studies in VR because it's difficult, or impractical, I would say. So no, I haven't done it. I'm not aware of it. But anecdotally, I can say that these illusions tend to, for us around the lab who get to participate in these all the time and do this, they just seem to work. Even though I know that this illusion is happening, that it doesn't seem to have a negative impact on the experience. It's one of those things that I think I can just accept because the experience seems locally consistent. So, yes.
As a follow-up on Michelle's question, do any of the subjects report any kind of unease in knowing I shouldn't be able to walk down this hall this far because I already saw there's a wall in front of me? Or do they kind of start walking slower as they get?
Not that specific, no. Not that we could tease out in any of the data, although they did report a general sense of feeling turned around. And I think that goes to your question, which was about, did they see the space beforehand? They knew, if you see the space beforehand, you know how big the tracking space is. You know you can't walk through an infinitely large space. So I think there is this general sense that I got turned around, but when we try to tease out of them, how did that work? How did that work? The overwhelmingly seems to be I have no idea how you did it. I just know that I've been turned around. So. Yes.
An observation on that, it was the earlier study, somebody else with the zigzag hall.
Yep.
I noticed in the first zag, you see a lot of movement there where that first time they get adjusted, you can see their brain was trying to figure something out. And then after that, it was pretty clear that the brain just kind of... Yeah. And this is a phenomenon called perceptual calibration. We know that it takes a couple minutes, and this has been studied in perceptual psychology, that people will accept you can actually recalibrate to all sorts of different things, like different walk speeds, different motions, even remapping of kind of the movements of your head along different axes. It takes usually a couple minutes, and then afterwards a couple minutes to calibrate back, but it's a very rapid process. Okay, any more questions about change blindness before I move on? Okay, so like I said, this illusion was unexpectedly powerful. So I started really thinking about other types of spatial manipulation that we could leverage in VR. And so for this one, I drew my first inspiration from psychology. This one I'm drawing on my nerd credibility here from science fiction. And so who here is familiar with the BBC television show Doctor Who? I love giving talks to technical audiences because they actually get this reference. So
for those who aren't familiar with it, in this kind of timeline or mythology, the Doctor travels around in this thing called the TARDIS, which is basically the size of a phone booth here, but the inside of it is much, much larger than could ever exist in the real world. In fact, canonically, it's supposed to be infinitely large. So this was the kind of basic illusion that I wanted to investigate in VR. I wanted to understand, I wanted to experience this magical sense that all the people in the show got whenever he leads new companions into the TARDIS and they go with a sense of awe. It's bigger than on the inside, and it becomes this joke. But I wanted to experience that sense of magic of walking into something that's bigger on the inside. Fortunately, in VR, we can create this. So here's the kind of experimental environment that I built to test this. So I use a kind of very similar environment to what you saw before, where you walk to desks and you're looking, we give them a task of going over to look at monitors to see pictures, because it's just a way of making people move through the environment. So you go through one desk, you turn on a picture, you walk down, exit a room, you walk to the hallway, and then by the time you get to the entrance of the second room in the hallway, the first room is essentially deleted and the new room is put in its place. And of course, if we look at these kind of superimposed on one another, this is a severe violation of Euclidean geometry and could never exist in the real world. So I wanted to now see how sensitive are we to these types of illusions? So the way that we figured out to do this is to do what's called a psychophysical experiment. So what we did was we just asked them we did these on whole different levels of overlap, ranging from 0%, which means perfectly can exist in the real world, to over 75%, which basically means like most of the rooms are completely overlapping and they're almost completely on top of each other. And we just had them give them this kind of discrimination test. They experienced a whole bunch of trials and we asked them, is this impossible or possible? And we do this over many, many, many repeated iterations, and then from that we can calculate the probabilities and generate what's called a psychrometric function. So I won't go too much into all the detail of this, but the point here is that this is the probability of being able to detect that it's an impossible space. And this is the overlap level. So this is increasing amounts of violations of geometry. And what we found in our data is that about 56% by convention is when they start to become reliable. And so you can get quite a bit amount of space savings by overlapping geometry, and people won't really be able to detect it if it's less than 56%. And the interesting thing is this is when people are explicitly told about the illusion and instructed to try. Really hard to figure it out. So I think this is actually conservative, and if you did this on someone who's completely naive to the illusion, you could get away with a lot more.
They walk in the corridor, they
Yes.
walk at one-to-one.
Yeah, the corridor is walked one-to-one, yes.
What happens if you sort of make it virtually faster? Would that make the understanding that this is a bigger space?
I haven't tried it. It's a very interesting idea, though. So yeah, you might be able to, because to some degree people are using their bodies as a ruler and judging those steps as a way of judging distance. Some of the people, I noticed some strategies in the study that some of the people who were really, really good at the task were actually counting steps. So
some people are just innately better at judging distances.
that is true. That is true.
The people that are probably the best at it are people that work the cameras for film directors.
Yeah.
They're amazing.
Yeah.
I'm wondering if you normalize against that.
I do take some demographic data. I haven't looked at that. I will say, so most of our subjects are actually not university students, which is a lot different from a lot of the way academic VR labs do it. We recruit off of the general population on Craigslist. So I had a pretty broad kind of selection of people, but not the sample sizes we're looking at are too small to be able to draw any conclusions about the population. The only thing really I can tease out is video game experience, but even then, it wasn't predictive of performance in this time.
Isn't LA just unemployed actors?
I might need to modify my demographic questionnaire then. So beyond just do they notice it though, I really again wanted to go beyond just that and understand kind of how does this impact your experience, because self-reports of I noticed this are only so useful. So for this, I came up with a metric which I kind of drew on from the VR literature called blind walking. And so this is a distance estimation test, to get at your point. So in this sense, what they did was after they walked to that second room, they were asked to turn back through the wall to where they saw the first target. So both of those desks were, as pictured there, kind of against the same wall. So they were asked to turn and to where that first one was and close their eyes and imagine how far away they were when they were standing in front of that target. The HMD at this point goes completely black, and then you're asked now to walk until you are physically standing on that point that you were. So that's why it's called blind walking. This is a very common metric used for distance estimation studies in VR. The difference and the caveat here was that in the cases of overlap, then the actual place that was would have been either forward of the wall, or in some cases, in the extreme overlap conditions, literally only a step or two away, like they were almost on the exact same space. So the question here was, would they walk to where it actually was that they were physically standing, or would they correct for the compression and continue walking as if those two overlapping rooms had actually been moved out and were actually now correctly side by side? So this is what we found in the data. And so what we're seeing here is overlap level, again, around here. And this is in percentage of the walk distance relative to what it actually should have been if it were accurate to the real world. So if they weren't correcting from the compression and they were walking to where they actually were, we would expect to see the data follow that 100% horizontal dotted line. The red dotted line is what we would expect to see if they were correcting for that compression and overwalking. And I love to show this data because this is one of the most clear-cut examples of an effect that I've ever seen. You really don't need a lot of statistics to be able to look at that and see exactly what they were doing. So even in the cases of 75% overlap, where it's really obvious, very few people, 90% of people were able to reliably detect that this was an impossible space. Even in those cases, they were still walking those exaggeratedly long distances when kind of in behavior correcting for this illusion. So I think that was a really, really interesting finding. And it kind of goes to this idea that I like to say that, like, we've learned that spatial perception is malleable, and that people, even if they kind of can perceive that these things illusions are going on, they'll still try and behave normally as long as it doesn't mess with their experience, or at worst make them sick. As long as you can make the experience still very rich and pleasant, then these illusions, even when obvious, could still be useful. But now I'm going to start to get more of raise more of the practical question, stepping out of the basic research hat and now start talking as a VR engineer. How is this actually useful in a real practical system? And so now, if you want to ding me on anything, you can ding me on saying, hey, these are really only work in these linear environments where you have this kind of purpose-built experience that kind of validates the technique. But if you want to give free-flowing exploration of just an arbitrary environment, how would you do that? These aren't generalizable. And I think they're not, like, there is no generalizable solution for a redirection that applies to all spaces at all times. At least we haven't discovered it yet. What they are is tools. They're tools for VR developers and VR designers and content creators to use for the experience that they're doing. And they're best employed when you can actually couple the content creation with the kind of experience and techniques you want to use. So some of the interesting ways we can use these tools. So this is an example of how we use it in a mixed reality setting. The change blindness technique is really interesting because it's a discrete change. It's unlike the motion illusions. This is not a continuous change. It's a single state switch, and so because of that, it's predictable. So instead of doing a 90-degree offset, this is one where I did a two-stage building where there's interior rooms, and what you're going to see here is when you get to this back room, I'm going to pull the same door switch here, and then this door switch is going to move over here. So there's actually two doors moving here, all behind your back. And what this essentially lets me do is reuse this road infinitely. So we trucked about 1,000 pounds of gravel into the lab, which I would not recommend for cleanliness because we were cleaning like dust for the next 3 years. But when you enter in a building here, and then when you exit the building, you ended up exiting here. And then every time you step right back onto that gravel road, you feel the crunch under your feet. You feel that haptic sensation. And so it was a very, very compelling illusion. Or again, that's that sense of magic for me, because now there's a sense of realism. The real world is actually kind of playing along with this illusion. Here's an example of another kind of way in which these impossible space techniques could be used in a practical setting. So this is a technique I call flexible spaces. And in this sense, what we're doing is we're playing with similar violations of non-Euclidean geometry, but we are doing it by creating twisty hallways that kind of curve back in on themselves. And so what we're doing here is this is an environment where each room is pre-modeled. This is researcher art, so that's why it looks so bad. But each one of those hallways is procedurally generated on the fly in Unity based on so the polygons are just generated as needed based on where you're standing in the space and where you need to go. And so the really cool thing is that you can just basically do this infinitely. And then, so I need a hallway that gets me to be standing over here. I can just generate a twisty hallway. And you do get a kind of a sense of like, again, that general sense of like something fishy's going on here. But because we're not employing any of these motion illusions, there's no real risk of inducing additional simulator sickness. So I think this is a really cool technique that could be used for entertainment and for experiences in general where the individual layout of the environment doesn't so much matter. So educational experiences, museum exhibits, things where you're trying to experience content, but the exact spatial layout is irrelevant to the experience. And trying to move this now to really into practice, I mentioned that ICT has a lot of DoD funding, so what we want to do is really, again, do the same thing we did with HMDs and make it possible for people, our funders, and also just the general public to make use of these techniques in this toolbox. So this is an example of a redirected walking toolkit, which we built for Unity. We actually have completed it, and we're actually just getting the website up. We'll be released by the IEEE VR conference in March, open source for Unity. And so what we're really doing here is trying to build all of these kind of at least more generalizable techniques into sort of a toolkit that's plug and play. So I can just hand it to a developer and they don't need to know about all the math and the perception. They just need to tell it how big is my tracking space, here's where I want to go in the environment. This was an example where we're actually planning waypoints. So we're telling it, this is where we want you to be able to go so that the environment can plan it. And then it will figure out the math and make that work. And one of the real reasons we're doing this now is because we're finally seeing a consumer level wide area tracking system with the HTC Vive coming out, which can get tracking in around 5 by 5 meters or so, 4 by 4 meters, something like that. And so it's really now you can start to see, okay, if we're not getting up to like the huge spaces, but we're starting to see consumer level tracking that can actually allow some movement. And I'm going to give you an example of how we use redirected walking using the toolkit within a Vive setup. So this is an example of an environment that we did for the SIGGRAPH AR/VR contest last year, which actually won first place at the contest. And this is in collaboration with our partners at the School of Cinematic Arts. So what you saw there was a turntable where we're working with stop motion animators. And so there's a rig that spins that around, and there's an image taken every second for every degree, and so then you're able to do kind of capture the image at every angle. And what we're doing now is doing image-based light field rendering within an HMD. So we created this experience for the conference, but then they said, oh, you've been invited as a finalist, you have to bring it to the conference, here's our demo space. And we're like, our environment does not fit within your demo space. And our environment, like the key to this stuff is really being able to move around it, because you get all these specular reflections and subsurface scattering and all of these really fine visual elements that don't come through in geometric rendering, but you really get from these image-based light field approaches. So that movement, that physical body movement around it is really, really important. So what we did was we basically went through, we used the redirected walking toolkit, and this is that same zigzag idea that the redirected walking paper from Chapel Hill did, but this is actually the physical kind of space dimensions you would get with a Vive. So now, as long as we give them verbal instructions, so there's a narration that says turn to this exhibit, and it explains linearly because there's a progression through this exhibit. As long as we're able to direct them to go where we want to go in this environment, you can see we put a couch here as a kind of visual indicator of the scale that this could actually work in a living room size space. And then, so interestingly enough, I do have this demo on my laptop. I know that there are some people with Vive setups in this building. So if anyone who has a Vive setup wants to experience this, I have some time this afternoon. I'm more than happy to come by and you can actually see what it feels like. And so that's an example where we know the path in advance. Another way of being able to deal with this path prediction problem is in letting the user plan a path. So this was one of our kind of early cheats, was that, okay, we can't really let you walk anywhere, but we're not going to tell you where to go in this kind of free-flowing environment. So we gave them an app, and they basically said, plan your route. And then we'll figure out the algorithm will then figure out how to get you where you want to go. So this is a little bit more free, but not totally free yet. Now we're working on the kind of totally free case. So this is forthcoming work that that's just been accepted to IEEE 3D will be published later this year. And what we're doing here is we're building short-term prediction graphs based on the geometry of the environment and where your movements. And what we're doing here is we're basically leveraging a tool that's already available in all these game engines for doing game AI, and it's navigation methods. So navigation methods are basically how game AI does its path planning. And so we're basically taking all of that technique that's built into all of this, and we're using that to essentially build up these prediction graphs about where the user is theoretically going to want to travel in VR. And so this was just the initial technique, and now our next step is we're building this into the predictive algorithms that we have implemented, and then we can measure the kind of expected performance or advantages of doing that.
Nav meshes in Unity are notoriously static, aren't they? I mean, are you able to dynamically change the level using nav meshes?
So I can't speak to that because we haven't, we're dealing with the static case first. We're not even dealing with dynamic yet. I do know that our preferred way to use nav meshes are not the Unity built-in, but using a package on the asset store that extends it. So I'm not sure about the dynamic case. And then another technique that we have in the toolbox here is a reorientation technique. So what happens if these techniques fail? Let me start this over again. So what happens is basically if we know at the very second that we tried to predict as best we could, but at some point you're about to hit a wall, we have to do some sort of fail-safe or some sort of way of intervening. And maybe this is one potential trick that may or may not work in a particular experience, but we ask them to take a panoramic photo. So this is an example where we basically just ask, take a panoramic photo. That's something that most people with smartphones now are familiar with. And what this basically does is it gives us an excuse to give them a spinning motion. But that spinning motion occurs on the spot, so we can basically do an emergency reorientation away from a wall. So again, it's disruptive to the experience. We don't want to do this too much, but as an emergency, when everything else fails, it's better than having to take off the HMD or crash into something. So you can see now how these kind of techniques work. We try to apply this continuously, predictively as best we can, but as they're going through the environment, if eventually they end up hitting a wall, that's when you see that kind of space spin around them. That's when we do some sort of reorientation technique as a fail-safe. So you can actually get through a city-sized space right now with a little bit of interruption. The reorientation techniques, though, do provide a great metric for effectiveness of for evaluating these algorithms. So what we did now to kind of move this forward as we're developing these algorithms more is we developed a simulation framework where we can tweak algorithm parameters and then generate procedural paths through environments of different types and distances and systematically measure using those reorientation techniques, those periods of failure as a metric, a minimization metric to try and get these algorithms better. I'll give you one quick example because I'm almost out of time. And so here's an example of popular ways of doing steering for any sort of like continuous system. So people in VR, they thought, okay, the previous convention was steer to center is best. We just kind of naively try to get you to be in the center of your physical space. Other people have said, well, maybe it's best not to go to the center. The algorithm should get you to just kind of orbit around the center. So steer to center versus steer to orbit was an argument. The steer to center people won out. And so it was kind of conventional wisdom says steer to center is always better. But when we started being able to do this simulation and go up to larger and larger tracking sizes, what we actually found was that the conventional wisdom was not true after a certain point. That as the tracking size increased, and I'll just highlight this here, there's an inflection point. So this is the relative effectiveness. This is a derived metric based on the probability of getting those reorientation triggers, those fail-safe techniques. There's a period of time where the steer to center algorithm outperforms it, but at some point there's a crossover and there's a substantial increase in steer to orbit with sufficient space is actually much better, and in fact hits the theoretical maximum of never having to do a reorientation sooner with a smaller tracking area than steer to center. So this was kind of an interesting paper we published at ICAT last year that was just one example of how we can use evaluation to better design these techniques. And in the future, what we're really trying to do, I think the holy grail for the redirected walking is not just one user, but multiple users, because now you don't have to just deal with the physical boundaries. You have dynamic targets. You want to have people not bump into each other, but if someone wants to handshake or hand an object to one another, you might want to converge spaces. So there's a convergence and divergence of individual spaces, which is a problem we've just barely begin to explore. And the question is, I know 5 by 5 meters is pretty good for redirected walking in some cases, but it's not going to work for multiple people. So how big a space do we need? That's the kind of the answer we have to look at in these simulations of how big, how scalable are these techniques. And I think this is going to be increasingly interesting once we can go beyond what a Vive system can do in the consumer level. And was one of the reasons there are many interesting things about HoloLens, but the tracking on it, the fact that it's all inside looking out and it's tracking on the device is something that I would love to see built in to a VR, a pure VR headset. HoloLens being a mixed reality device is somewhat different. And these techniques don't really translate well to that kind of realm because you can see the real world. But then you can start to see if the device can just track me, I don't need infrastructure. Can I just go out to a parking lot, a football field? I can just make ad hoc use of big empty spaces, and then you could start to think about, okay, I could theoretically see a multi-user system like this working. But the tracking technology just needs to catch up with our dreams and our goals. So with that, I'm just going to wrap up. Like I said, VR for me, the real power and the reason I chose this field is because of this creation. You can really create magical experiences. You can transcend the laws of physics, and you can do things that you can't even dream about doing in the real world. And that is something that I think is just we've barely just, it's just the tip of the iceberg in terms of what VR can do. And the other thing is that at the role of researchers, I think it's really interesting that this is from a blog post earlier this year where someone, a random VR hobbyist, was thinking about the Vive, and he saw the Vive, and he was like, what can I start to do in a Vive? I want to go through a larger space. And he actually started sketching out things about walking along circular arcs, walking in 90 degrees. He hadn't come up with the idea of mirroring it to rotations or employing illusions, but the hobbyists and the kind of general public doesn't perform literature reviews, and through brute force, they're rediscovering, with a little bit more thinking on this and work on this, they'll come up with redirected walking. So as researchers, that's kind of the goal, is to kind of create toolkits now and kind of inform the general public so that they don't brute force it and invent the wrong thing. All right, with that, I'd like to I should acknowledge that this is the work of a lot of my students, PhD students, interns, undergrads, engineers, and so work of a lot of different people. With that, I'll take any other questions. Yes?
Are we doomed to walk in VR, or at least 25% faster than usual?
I think I don't know if I'd call it doomed, because One of the things that I do think about in VR is energy expenditure and fatigue. I think that it would be great if I want to go through a large space and I don't have to walk a mile and I only have to walk 3/4 of a mile. Unless I'm trying to get exercise, at which point you might want to slow it down and then get a higher distance. But it's not always a bad thing.
No, but then you will get the problem of inconsistency between the senses, right?
Yes, yes. Although, like I said, certain amounts of inconsistency is tolerable. And in fact, not just tolerable, but imperceptible. And that's not an attention thing. That's actually a more when it's a perceptual effect. It's so low level that it's actually more. It's more of a brain thing than it's not a level of your attention. Like if it's imperceptible, you can't. It's really hard. You can't even do it, even if you try. But of course, individual variation exists. Yes.
I have a question, observation about the gravel path demo you showed.
Mm-hmm.
That adds a very strong constraint to your system, so that really won't work with free walking, right? Because once you exited the first building and came back to the path, if you had gone back, you would have stepped immediately like outside of the bounds of the room, right?
Right.
So, but you can use different cues, like audio cues, right, to simulate that he's walking on a different type of surface, even if he doesn't physically feel it. Have you done anything with that?
Yeah, we've done audio. We've played around with audio sounds, like the crunching sound. The other thing I played around with was actually trying to build shoes, which had a layer on the bottom that actually gives you like different sensations on it, or could even. We tried to cut it at an angle to kind of twist your foot a little bit in a direction and bias you towards walking a little to the right or the left. Turns out that works when you close your eyes, but when you're walking, your vision dominates and you just try to correct for it anyway. So it didn't work out as great. So we tried to look at a bunch of different ways of being able to do that. But to your point, yeah, all of these techniques have different limitations in terms of generalizability and when they would be useful and not, and different ways of being able to violate those assumptions. But the point is that each of those techniques have different assumptions. So you pick the ones that are best, and in combination, you could potentially get away with quite a lot. So
that's true for all the variables, right? I mean, like the level of fidelity, you were mentioning this is a research-driven, research-drawn space. If the level of fidelity had been a lot higher, it would have, in the whole equation of comfort, it would have probably mitigated against other things that were created discomfort. Does that make sense?
Yes, yes, and in fact, I think I think some of this is actually empirically needs to be measured when we get to these systems that can render at greater than 90 hertz and have really low latency tracking, because some of the things that were intolerable or just not really, or things that were good before, techniques that were acceptable because they might have been masked by latency and jitter, might not, and we need to reevaluate them under these new circumstances. So, yep.
Most of the measurements that you do are kind of verbal scores in some sense, like, have you noticed it, have you not, did you notice, where was the door? But I've noticed in one of the pictures that you had kind of EKG hat on and wearing the headset. Have you thought about any more kind of biological sensing or electrical sensing of that what people might not report being noticeable, but actually is noticeable by the brain?
Yep, I haven't personally. There are people at ICT who have done that. I think they tend to be more in the medical VR sector, and so I think that there's all these. I think a lot of difficulties with doing this with large-scale walking because there's all the physical movement. I haven't personally done anything with brain scans, but I have, over time, I've become less enamored of using verbal reports and subjective measures, which is why I started to use things like those distance estimation studies and started to look at designing experimental tasks where if I can't go for a psychophysical biological signal, I can hopefully get some sort of objective behavioral signal, and I can measure user behavior instead of relying on just a self-report, which has all those problems.
So far you've assumed there's sort of an empty area. Have you looked at any, like having objects that the user would need to avoid, physical objects, and redirecting them around those objects? Because I think most living rooms or houses could be a lot larger if you can force them to kind of go through from room to room as they walk around?
Yeah, I think we haven't really, as a field yet, tackled that. We've just started with our evaluation framework to start testing non-square spaces because we started to realize, wait, there's no reason why these have to be squares. In fact, ours is rectangular. So we're starting to look at different shape and how shape affects the size, because shape is actually interesting because you can get long walks in one direction, but very short walks in the other. To look at obstacles like that, no, we haven't really done that, with the exception of Love Coley's work, also from UNC Chapel Hill. So about 5 or 6 years ago, he had a paper where he tried to combine passive haptics with redirected walking. And what he did was he was using the rotation techniques. So he picked cylinders because they're rotation invariant. So he could put like a cylinder, and he would what we do is redirect someone, and then they would always the space could be circularly or rearranged around it, but he could always reach out and touch the circle or the cylinder in the space. But navigating around obstacles, I think, yeah, that's not a area for work. It is an area for future work. Yep.
Okay, Alex. I had a clarifying question for myself. I couldn't remember. In the first part of the talk, as people are walking what they think is straight, do you sometimes curve as they're walking straight, or is it mostly that you do the variation as they turn themselves, like when they hit a wall?
They're two distinct techniques. Rotation gains are done during your rotations.
Right.
Curvature gains are done when you're walking straight.
Okay.
So you're walking straight, and there's just a slight continuous rotation that gets you to bend your path. And both have their own thresholds. But they've always been measured separately. We actually are now doing a study where we're doing them simultaneously because we think that there's a combined effect that hasn't been empirically measured yet. But they are two distinct ones. Yep.
Is there anything interesting to say about vehicles? So if you had a Humvee sitting in your lab and you hopped into it, started it up, and drove someplace, and then got out, I mean, I guess it's not that interesting to you. I'm wondering if there's something else to be done in that space.
I haven't thought about.
I was thinking about that as one of your examples had a Jeep sitting around.
Oh yeah. No, that was just a simulator. I haven't done anything research-wise with it. Because I think once you exit the vehicle simulator, once you enter and exit, you can be in completely different places virtually.
It may not be that interesting. I mean, it might just work.
Yeah, I think we've been asked actually. So by the perceptual manipulations that we've been asked to consider are more about, when it talks to vehicle simulations, are more about haptic control surfaces. So the Army, for example, wants easily reconfigurable simulators for prototyping. So they want to be able to do VR environments that can have these kind of dynamically repurposable haptic surfaces. So that's kind of where I see more perceptual manipulation potentially being employed.
Well, thank you very much.
Yeah, thank you.